This is a cloud-based application for evaluating the performance of a sequencing batch reactor based on the inputted field data and determining what the time should be set to. You'll see here in the explanation that there are three scenarios. You'll see that the first two employ the inputted parameters to show the difference between a good batch and a bad batch, which I call the previous batch paradox, because if it's too high, it impacts how that will react and how long it takes to recover. The third method employs regression analysis in order to determine the time needed for the parameters inputted. We'll go down and pass the instructions and come down here to show you the input screen for this app. In this particular case, the input parameter is 24, and we'll assume that this maybe is ammonia, because you can use this to set the aeration time for ammonia, the mixing time for nitrates, and so on. So we have 24. Based on the input data that we have, this says that because we have a batch volume, that translates into 7.39 at the start of the batch. The end concentration we desire is 1. The end time is presently set to 70 minutes, and the settle time is set to 45 minutes. The last batch, which is an important parameter, I have set to 0.5. This would be whatever the previous batch was. Mixed liquor is 1900 because you work off of the removal based on the mixed liquor volatile suspended solids. In this particular case, the batch volume is 15,000, not the total reactor volume. We're down here and we see that we got a length of 60 feet, a width of 12 feet, and a side water depth of 9.5 feet full. The app comes down and tells you that we'll rate the input 70 minutes. We come up with a removal rate. We come up with a mass loading. We come up with the pounds of volatile suspended solids. It calculates out the total volume of the reactor. It calculates out the pounds of material removed. It gives you the end batch, and the decant depth is 2.79 feet. And then the app calculates out the equivalent, because you're decanting, the equivalent of a surface settling rate. Okay, in sequence 2, it's the same thing. We kept the batch volume at 15,000. Now, all of a sudden, we got a slug of 35. So we go through, we increase the starting concentration from 7 to 10. We kept the mixed liquor the same. We started with the 70 minutes again, and then we come down and we calculate out the new mass, the removal, the mass at the end, and you'll see that the sequence time increased to 106 minutes. So if we did nothing, we wouldn't remove enough to get to the 1 part per million. Now we're in the scenario 3, which is what we're doing is we're entering the concentration over, let's 70 minutes, and we sampled, and we could do this with a sequence sampler if you weren't there, or refrigerated, and we got the values for the parameter versus time. So we enter them into this table, and then you come down here and you say, okay, desired parameter concentration is 1, and under these conditions, using the rate of removal, we need a sequence time of 59 minutes. I can change this to 2. Solving. And since the concentration increased rather than decreased, it decreased the amount of time that I needed. This is all based on regression analysis for this data, and you can see that we have the two charts that show you the removal rate versus the time. So this application is pretty handy for determining what your timer should be set at in an SBR plant.